These two are these rush bar states. The bulk touch. After bulk touching, then bulk separate, and then you have one go here, another go here. Like here in this case, if suppose far enough, go to another. Suppose here is gamma, here is another time reversal invariant point x. Here they touch here. They should like touch somewhere and separate the pair. And all in a way, we see a system if we only at the surface. We plot the surface band structure. Suppose this is x, another x, and a gamma point. And we and actually, this is what happens. This is the dispersion. This is the energy for the surface states. And well, suppose the bulk state is somewhere. This is the bulk. They just evolve into the bulk. This is the Kramer's degeneracy. They're always degenerate. Then this state start from 1. Maybe it crosses many times, but you see, it always like here. This state, they are neighbors. They are degenerate here, but then they separate. Later, it will degenerate here with another state. Here, it will go to a different partner. What happens for rush bar states or normal surface states? It will be at the beginning, two states are degenerate, but later they will meet again somewhere. And even they are go to very different energy, whatever. Oh, interesting. And this is what happens for normal surface states. This is what happens for topological surface states. Like their partner, they split and merge with another one. And then this keep is always going this way. And this is a trivial one. And then, but however, when you only observe a small window, like for example, this point, around this point, and this rush bar states and this topological surface will look just quite similar. For example, only here, you also see here some upspin, downspin. Here, actually, you cannot really distinguish them. That means if you want to really identify, suppose you have experiment result or theory result about surface states. You calculate, you get a surface band structure. You should look all the Brillouin zone, at least from one point to the end to the boundary of the Brillouin zone, to see whether it really goes from the valence and connecting to the connection band. But if you only observe a small window, there's small part. In principle, they're not very different. You might, yeah. Yeah. For which one? Which material one? Yeah. No, I think they're quite reliable. They're reliable. Previously, but photon emission can show you the information with all the Brillouin zone. That's no problem. Yeah. And I just mean, don't focus on small region. Topology means it's the information from the full band structure, not a local one. Yeah. Or sometimes people claim like this topological system you cannot realize by a small or some local parameter. Actually, it's related with the full system. And yeah, this one example is more. Yeah, then reason some interesting thing come here. Suppose this is some trivial states. Then complicated is actually commonly happen when you have a topological state, they mix together. What can happen? And although they come from different reasons, actually they do hybridize, because they both live on the same surface, And when electron travel, and it can be scattered from one state to another, right? And then what can happen here? And actually, what will happen, there will be some detail. Just you assume at this band touching point, they open some hybridization gap. And you will get a band structure from this way to that way. And it is clear from here to there. Yeah. And here, different color, you can treat different colors still as different spin polarization. And then somehow, you can call locally this point is a Dirac point because there's band crossing. And here, this point is another Dirac point, right? And sometimes, if this hybridization is strong enough, yeah, suppose this is the most simple case, and then you have another band here crossing. Then after this band, okay, every band always have spin up and down because we have this time reversal. And after hybridization, you may realize something. Here, there's strong hybridization. And if you only observe here, they just look like very perfect isotropic Dirac point. This can happen in some materials, but it's not necessary to argue too much. We have one Dirac point or two Dirac point. And the most important topology is this state. We are always connected to the end. And yeah, it's different. Yeah, for example, this one is trivial. But in the reality, when you observe the real system, everything mixed together. And the most important topology, you should trace the direction from the valence band to the conduction band. It's still, yeah. I just say topological surface states and trivial surface states, they will have some interaction, like hybridization together. No problem. But after that, it's still topological. It does not change this connection. And, this is another example. If suppose we have a normal insulator or metal, whatever, it might have surface states. And its surface might be metallic. And we also know, in reality, the surface, there are a lot of dirt or oxidization. They can be quickly oxidized. And what will happen, like for normal states, you oxidize it, and then it becomes an insulator, just killed. And for topological insulator, what might happen? You oxidize the top layer, then okay, this state disappear, but then you create a new interface between the top layer and the bottom bulk. Then here, in this region, it's still metallic. This just means when you oxidize the top, you kill it, but it just sink a little inside. And another weak way is just hybridize with some another states, make it very complicated, but the topology doesn't change. Then in this sense, we see several possibilities, like how these topological states becomes very robust. And another I didn't mention is, like, when we talk about the quantum Hall, what we really like is this quantum is these edge states cannot be better scattered. Later, we talk about there are two quantum Hall together. However, when we put them together, we have two edge states, one left, another right. Are there possibilities to have scattering? Yeah, if there's scattering, then it's different. It has there will be strong resistance. And actually, they will not, because these two states, they just have a different spin. And they have opposite spin. It is scattered back. You have to flip the spin. For example, you might apply some field or have some magnetic impurity. Otherwise, it just go there. Suppose we have impurity, what will happen? And in this case, this just circling around. Here will be similar. Just there are no state to scatter back. And then that means topological surface states or edge states are not also strong against the back scattering. And then people assume, actually, yeah, for a while, these edge states will be robust and in transport. but later when we go to the material, we will see in reality how complicated it is. Okay, here this cartoon, yeah. Yeah.
How much does this affect the backscattering interaction? Especially in three materials where
Yeah, it's still scattered. It is still protected because, like here, from the color, you see the left mover and right mover, they still have opposite spin. This doesn't change. Yeah. And this is a short summary. Like for topological insulator, we have 2D version and 3D version. And we repeat for 2D version, like here, same. In the middle, the 2D plane, the plane is insulating, but on the edge will be metallic. Then the edge, the left mover and right mover have opposite spin. We have these 2 copies of chiral edge states. In the literature, people also call it helical edge states. And the helical simply means like the opposite spin, they move oppositely. There are 2 copies together. And for 3D version, we have an insulating bulk, but on the surface it's metallic. It means on the surface means every surface, not only the top, the bottom, the side surface. As if you cut it, you create 2 new surfaces. Both parts are metallic. And then they are very different from like a normal insulator, or also very different from a normal metal. And insulator does not conduct, but the normal metal is conducts everywhere. And then this Dirac structure, like, well, we are very familiar with the Dirac in graphene. Then what's the difference between this one and the graphene Dirac? And graphene Dirac, we know, like, first, graphene Dirac has spin degeneracy. When we derive this Dirac crossing just from in the honeycomb model there, and actually it's a spinless case. If you consider spin, it's spin up down with same band structure. And then for graphene in the Brillouin zone, actually, there are 2 non-equivalent Dirac in total in the hexagonal. And then in total for graphene, you have 4 Dirac actually. And then, however, for topological insulator, this Dirac just simple 1. And this here, this spin chirality, maybe see this one, because everywhere spin and momentum are locked. That means every state has only just 1 spin. There's no another copy. And then there's a single point. There's no another valley. And all, in other words, in a complete case, there will be always odd number of Dirac. And we will see the reason later. And then that means this Dirac simply is just a quarter of graphene. And so far, this material, like, then in reality, these states can be realized? Yeah, sure. Then the first one actually was realized in mercury telluride. Yeah, where, in this, like, it's a 2D quantum well structure. And here, the edge state was observed in transport. And later, there are more and more materials have been discovered, especially this family, bismuth telluride family. And then later, many material. I think so far, there are like more than 200 or 300 materials, at least predicted by theory. And yeah, I think more than 30 have been already verified by the experiment. And then it's no problem. These materials, this kind of topological insulator states appear in many materials. Actually, it's common. And for example, like here, this material, bismuth telluride, bismuth telluride, this material, they were known for many years for different purpose. People studied, for example, for thermoelectrics. And for many years, just did not recognize they have special surface states. And then a little more about whether, yeah, anyway, all the time people ask whether they can, there's some application. And one is about, like, since we mentioned here, this spin and momentum, they lock together. When they're moving to the left and right, they have opposite spin. Then it's very strong against the backscattering. Then we might expect here the conductivity of this system might be very good. And however, in reality, it's not that perfect. But Another important information is like, you see up and down move in opposite direction. This already exactly tell you this is a pure spin current. In this case, the system will carry just 100% polarized spin current. Spin current means like we know if system only have spin up, it's moving. We know it carries a spin current. And then if we spin down, moving to this side and that side, they are together. They double the spin current, right? And then, well, there are others like I think until today, still the most important object of this field. People want to find a Moderna Fermi, try to use this topological surface states and make this surface states superconducting. But I will not touch this direction too much. And here, let's see some example about the band structure, or talk some example about the topology, how it happens, and then how it's related with this band structure, the detail, or how this topological number is defined. And then we go to the early idea of graphene, as I mentioned on Tuesday here. On the graphene, the smell coupling is introduced on the second nearest neighbor hopping. After introduce it, we get a gap. And in theory, there's a tiny gap. And we suppose we just assume there's a honeycomb material, maybe not necessarily graphene, and it has very strong smell coupling. Then it will be a gapped one. And in the gap, now let's have a slightly look about the band structure. Actually, for graphene, we can also plot the band structure like by hand. We see this honeycomb lattice, and we know carbon has 4 valence electrons for the carbon atom. Just see the carbon atom. It has, what's this? 2s, 2p. They're just these electrons. And if we put carbon atom into a lattice, then what is the unit cell of graphene? Actually, you see this A1 and A2, just the simple unit cell, the primitive unit cell. It includes 2 carbon atoms inside the unit cell, like this. There are 2 carbon. You repeat them periodically, you will get this honeycomb lattice. And then there are 2 carbon here. And let's simply look at if we put 2 carbon atoms close together, and what will happen. We know this is the s orbital. This is the p orbital. We don't think about spin now so far. We just use a spinless model. And there are 2 carbon. They start to hybridize. And sure, s orbital, they form, what will happen actually? S, they may do something. They form some bonding, anti-bonding, but the energy is much lower. And then let's look at the p orbital. Actually, when they form in the plane, suppose this is xy plane, they form a bonding. Then the px and py orbital, because they are in plane, they are strongly related with this chemical bonding. Then, suppose you have an orbital here, you have another orbital here, they form a strong bonding, right? And then the px, py energy will be very low. You will get, we simply call it here. This is xy, this is very low, very high. And then this is xy. After the hybridization, you get this is the bonding state. Then, since this is a very strong bonding, then the anti-bonding state, its energy will be very high. Y star. Yeah, that's it. This is for the xy. Then you still have the pz orbital. And then what is this pz? Suppose we plot, this is z direction. This is x, this is 2 carbon bonding. This is the pz orbital. Right? And this pz orbital has 2 type of ordering. This is opposite. Then obviously, this is the bonding of this pi state, because here these overlap are positive, and they slightly form some weak bonding here. And however, here is anti-bonding. Then that means, yeah, usually people call it this pi star. This people call it pi bonding. This is pi star because this is anti-bonding state. And then it's very clear. Like we also say this way. Then that means if we plot these energy levels at the gamma point, what will happen? Yes, Z. You will have pi star. This is pi. This mainly is band structure. Then how many electrons? And actually, we have 2 carbon, and then there are 2 plus 2. We have 8 electrons. If we put each level 2 electrons because spin and up and down, then you have 1, 2. How many? Then now you have 6. Then you need to put 2 here, right? Then you generate a gap here, a band gap. This is exactly here at the gamma point. Oh no, here is the gamma point. No, here usually when we write the tight binding model, actually this model here, this model is mainly use this pz orbital. Just each side has a pz orbital or s orbital. It doesn't matter much. This is just hopping parameter. Actually, it's mainly corresponding to here. All these bands just kicked out because they are far from the frame energy. This is true for the material. Then let's look more detail about here. Now we know if we plot some dispersion, then we have the momentum. Like suppose we go from here, the gamma point to the K point, just to the edge of the Bernoulli zone. And here is the pi state. Here is the pi star state. And how will they disperse? And we know if we write the broad wave function in the basis, like how this is, there are 2 carbon atoms, right? Then you will get 1 atom, like how it looks like. Its position, 1 plus. Okay. This is the bond length. Suppose bond length is A, and this is another. Yeah, you're right. There's some on-site energy, something. And this is simply, you can write the wave function in this way. This is just the linear combination with the atomic orbitals. And this A, this phase comes from these 2 atoms. They stay at different position. The distance is A. If at gamma point, K is 0, there's no difference for these 2 states. Then they form 2pz, it's bonding state, no problem. And then let's see the evolve. Like this one. Here, you have bonding in this way. If we go to the boundary, suppose here, M point. Here, M point. Actually here, chi corresponding to like one half position. Then you will get a phase of pi. Since you get a phase of pi, then you flip the second pz orbital, and you get it will look like this. It's orbital bonding. Then it becomes anti-bonding case. Then its energy will be high. Simply tell you, and the bonding will be high. Then for sure it will go to a direction like this. It will just disperse out. This one is opposite. It disperses down. Oh, not that much. Let's see. This is the M point. Then if you keep going to the second gamma point, yeah, just recover the case because we know it's periodic. Then they simply tell us we already know here. These 2 bands should cross somewhere. And actually then because of the symmetry, the details, the crossing point at chi. Actually in graphene, if you break this honeycomb symmetry slightly, like you push a little string, like make the A1 and A2 slightly different, and you make the symmetry lower, actually you simply shift this touching point from K. K is a high symmetry point away to somewhere, slightly. But you cannot kill this point if you don't include smaller coupling. And then this is a so-called Dirac one. We always see people plot in this 3D way. Yeah, this is the band structure of graphene, only near the frame edge. Then here, let me change the color, what we see. There is a, what's this? Actually, this is a typical case of band inversion. That's two band cross. Just two band cross. And how much they cross and how it looks like, maybe here is turn, how it looks like, just detail. But most important information is at the gamma, this order, the band order and the M point, they are opposite. For sure, here we have a band cross. We have a band inversion here. And that means graphene has a band inversion. And this band inversion will have some consequence. And suppose here we go to the boundary. Now we don't include the spindle coupling. We just go ahead. And suppose we make graphene this 2D system. We create an edge. And like here, this is the zigzag edge. And when we create the edge, please look at the symmetry here. This band crossing is from like chi to another chi, like actually it's crossing here. Along this line, you see, along this, the edge line of the hexagon, and you will have this band crossing. And then when you project to the edge, this crossing is still there. Like here, this K point will project to this point, and this K point will project to here. And this inversion band structure is still there. Well, this is bulk. Let's project it to the surface, to the edge. In the 1D Berlin zone, gamma is still gamma. Now we call it gamma bar. And M will be 1D, just Z. And this is another gamma. And chi also project out, no problem. And here, another chi project out. Then we still have the band crossing. And here, this region is still crossing region. And if suppose we only look at the M point and cross the M point, you plot a band structure. Actually here, you see it has a gap, right? And at gamma point, it also has a gap. And this 1D system, like suppose this is a 1D chain. Oh, sorry. You think about an infinite 1D chain from top to the bottom. Then project this chain to the edge. At the gamma is an insulator. At M is another insulator. Only here is metallic, only this point. And actually here, because here this insulator is inverted, the band structure is inverted, then the consequence is it will have metallic edge states or end states. There will be an end state here. And actually in all this inverted region, you will find an edge state. And this edge state is closely because of the inversion in this window. And then this example tell you have this inversion, exactly you have some edge states. And here we don't include spindle coupling. Just simple argument is not very different from our early argument on the boundary, like these arguments. And the only difference here, we have a gap at the band touching point. But here we don't have a gap. But what locally happened here doesn't matter too much for here, right? And then this we experience, okay, we have an inverted structure, we have a gap. And such kind of edge states, actually it was reported in the graphene literature a lot. You see a lot, graphene zigzag edge. For quite a while, people want to realize such a zigzag edge. And because there are some edge states, and then these edge states, well, later people call it there's some spin polarization. If you apply some electric field, it may become AFM, and there are a lot of arguments. And then, however, first we should all this discussion, there's no spindle coupling involved, or the edge states are already there. If you do the ab initio calculation, you create an edge, you will see this edge state. However, what will happen if we go to an armchair? Let's go. We go to armchair, this side. When you go to this side, these two K points, they project to the same point. And then you will form a single Dirac cone there. And actually, from gamma to x, except x point, the band order doesn't change. Looks does change, right? From gamma to x in between, still blue is below. And about here, red is below in this small window. And this makes difference. Then in this way, there's no edge states between gamma and x point. And there's also people talked armchair graphene ribbon don't have edge states. And then later, let's go a little more. If we tune on smelled coupling, what happens? This one? Projection, you mean K1, K2? You mean here project this Boolean zone to the boundary Boolean zone, you mean? How? Okay, maybe let's repeat it. And this projection, just a projection, suppose we are familiar with the Boolean zone usually plot in a way of this hexagon. If you, what? Oh, you're right. Thank you. Here, this is a 2D case. If you want to project to the 1D direction, suppose to this direction, all that. If you project to this, they just go here. Like this is gamma, gamma go to gamma. And this is chi, suppose this is chi prime. This, go to another, if whatever you want to call it. Yeah, and if this side, you just project in this way. And here, I want to see, here is another chi, right? Maybe opposite. Then here, that's all. Yeah. And then, yeah. What do you mean? What is A and B? Oh, here. Yeah.
I mean, program, you're doing some different projection because I've got the feeling that your projection in one case is along one of the axis and then one case is the other.
Yeah.
You get different results, and this is different strategy.
Well, obviously, your system, if you say system, you cut edge, the atomic structure of the edge looks different. Then they might have different edge states. This is reasonable, right? Then I try to explain this. These different edge states may come from the bulk projection. Because you project to different direction.
Can you specify what is the direction of your projection? So say, if I get my basis vectors, can you write basis vectors?
For
in your reciprocal space,
yeah.
Basis vectors. And just want to see what is the projection with respect to these basis vectors. Can you show?
Projection of basis. You mean the basis vector of the Hamiltonian?
I mean the basis vector.
Just x, y, z. This is kx, ky, kz. Yeah. This is.
Just indicated on your diagram.
Yeah, and here, suppose we project to the kx direction. Yeah. To the kx axis. Yeah. Just that. Just. Yeah, no problem. Then let's think a little more. Here, we already say if we see some region, oh, sorry. Where's the, keep it. For graphene case, we see some region. If the red is below the blue, we call it inverted. This region, it has edge states. And here, what we are talking, always like, we assume the spin degeneracy everywhere. And then, also for this edge state. And when we turn on the symmetric coupling, what will happen? What we already know is in the bulk. We turn on the symmetric coupling, the bulk Dirac horn will open a gap. Yeah, like here. Or this term we talked. And here, it's because of symmetric coupling, we get a gap. And here, let's see, it's a gap now. Then what happens for this state? Suppose there stays at the beginning, there is no symmetric coupling. We will turn on the symmetric coupling. And we are familiar with just the band degeneracy will split, right? And this band will, like, original is this one, up and down. Later, it just split in this way, up, down. Split in this way. Then we put it back. Then this is the edge states of graphene. It just looks exactly like a topological insulator. Actually, it is. And then for graphene, yeah.
Why don't they split being part of it?
You mean this way?
Yeah.
Yeah, very good question. Important is here, I will explain here, this gamma point, it has time over symmetry. Here, these two bands must touch. Somewhere, maybe they can also touch, but not very important. But here, they must touch. Then this is a natural choice. Yeah. Yeah, maybe they touch many times, but whatever, this point must be there. Here can change. And then, this is a, do I have a figure? Oh, yeah. Maybe let's look at this. And I see a little, now, actually we get an inverted Dirac horn. The Dirac horn, actually, Dirac horn just locally, you see some Dirac horn. And if you observe the full band structure, we see a band inversion. And this band inversion gives you this edge states. Then the consequence is like, we can understand it in another way. I think we already learned this SSH chain. And what is called? How to pronounce this name? How to? Okay. Many CH2 is a CH2 chain, right? Then if we just look at the graphene. Actually, this part, actually, it's a chain. Together, if we see this zigzag edge, actually there are just many, this C2 chain and connect together. And it's
Is band inversion a necessary assumption condition for edge states?
has what for what?
For edge states?
Edge states. Yes.
No, do you always have edge states if you have band inversion?
Good question. Easy answer is yes. And then if you have many inversion, they project together, then there will be another problem. Like these edge states can cancel each other. This can happen. But simply, you can assume just you have inversion, you have edge states. And you have this many 1D chain. And the SSH model tell you such kind of chain will have an end state, right? If you put many chains together into a ribbon, they form a ribbon. This end states at the boundary, they will form a 1D edge state. Is this one. And we just go a little more, is we add spherical coupling, it splits in this way. Yeah. But here, I just try to say is like, actually, for graphene, how this Dirac coin looks like is not the most important part. Well, there's a lot of another different interesting physics there, for sure. And also, there's a very easy Hamiltonian you can write down and play with it with a very different model. But if you think about topology, it's just a detail, not very important. Most important is here, these pi band and pi star bands, they get inverted in some part of the Berlin zone. This inversion is the consequence of the edge states. And then let's come back to the case. Yeah, this is the first Kim Millie paper. They demonstrate on the zigzag edge, indeed, there are topological edge states. And these edge states, when we plot this, like usually this calculation corresponding to start with the ribbon model. And then the ribbon actually has two edges, right? The left edge and the right edge. And these two, at each edge, there are two edge states living. They are traveling oppositely. And like this plot here, and the other edge, there's another two. And here, because here this system has very good inversion symmetry, and then in the band structure, they are just fully degenerate. What you use, if you only look at one edge, and these edge states, there's no degeneracy anymore. And now when we mention about like the Dirac coin, the spin chirality, and its log to the momentum, we'd better only think in one edge or one surface. Yeah, don't mix it. And then now let's come back a little to here what I mentioned, the armchair edge. And without spell coupling, people always claim there's a band gap. There's no edge states. Then what's the real case? Actually here, since we already know, we roughly believe it's a topological insulator, then edge states should appear at every boundary, right? And then at every boundary, then the armchair should not be a kind of exception. And then the armchair case is here. First, after projection, the band structure looks like this. And there's no inversion, sure. And then let's see. First, understand why, without smaller coupling case, many armchair ribbon people claim there's a gap. There's a gap, but there's no other edge states. The reason is simple. Like when usually the nano ribbon it's just simple the finite size effect. The bulk originally is a metal and it has a Dirac crossing, and then but you make it a finite size. The left edge boundary can see the right boundary. Then this finite size simply open the gap. Then that means usually people talk about the armchair ribbon, the gap, just the finite size gap. And there's no other surprise. For any other material, in the finite size, even metal, it may becomes a semiconductor. And then when we turn on the smaller coupling, what will happen? And in the bulk, we know all the Dirac coin get a gap. After projection, you still get a gap. Actually, here, you will see the edge states, the topological edge states. This is a purely topology. And then here there's something, like if you look at this state, and like how do we all in other cases, if we know some states, we know some band structure, how can we claim this is edge states, this is a bulk state? And commonly we just pick out the wave function here, pick up the wave function, and see the real space distribution. If you really say, suppose this is the boundary, if you really see this state very localized in this boundary region, okay, we say it's edge states. It localized on the edge. And then here is similar. And what you will observe is like this one here. Actually, it's very localized. However, that one might be very this way. And like see, this one is thick, it's wider. And this one is very narrow, very localized. And what is related? Actually, it's closely related with, for example, if you look at it here, closely related with the gap, the bulk gap in this region. And if you look at it here, actually, it's already, like that means they are at closing energy, there are much possibility it hybridizes with the gap. Then this one becomes wider again. And this tells you, like you have a topological surface space or edge space. It has some thickness. This thickness closely related with the bulk energy gap. If you have a wide gap material, they might be very localized, just on the top 1 nanometer thick. And if the gap is super small, then you get like it's just well connected into the bulk. But as long as then that tells you like if you want to, in theory, or in a model like here, you want to simulate edge states, you'd better use a very large enough ribbon or surface model. Otherwise, two surfaces will talk to each other, and you may miss the most important information. Actually, this indeed happens in the history. Okay, here, I don't go there too much. And then let's come here, how to really define the topology. Here, I keep repeating this simple picture of the band inversion. Then the question is how we really, in a good way, quantitatively define the band inversion. How much time I have? Oh, 5 minutes. Oh, okay, good. Yeah, good. Then maybe we come back later to this question. And then here, later, there are many different ways to really define the topology. Like, well, this kind of inversion we can observe by eyes. You can plot S and P orbital, but sometimes the situation is always not so easy. And easy case, less more simple cases, you have whether in this case you have inversion or not. If your only possibility is you observe some symmetry of this, then however, what this symmetry means is S orbital or P orbital or other property of the wave function. And later I will mention it's closely related with the parity of the wave function if the system has inversion symmetry. And okay, then yeah, let's start later from this.